All right, one of the big mysteries that I have is I give these charts, and then I tell somebody, okay, we're going to do hydrofluoric acid plus this, right? And the big mystery to me is how could they get the charge on fluoride wrong when I give them that chart? You know, maybe, I don't know, but maybe it's the stress of the exam or tunnel vision or something, but how could you write a -2 charge on fluoride when you have it right in front of you? You know, that's always been a mystery to me. Or how could you get the formula for, let's say, dichromate wrong when the formula is right here? I mean, it's no mystery. I didn't make it. If I put, like, chromate, okay, sure, chromate, you don't have it on the chart, but if I give you dichromate, how could you get it wrong? You know? And I know there's tunnel vision when exam time comes, and it's hard to, you know, because there's the stress of the exam and everything else. But I mean, people, I don't know if people notice this, but sometimes, like, on the practice exam, there's an example of this. On the practice exam, you needed the mass of deuterium, but, you know, I don't want to write it twice because I already wrote it once before, the mass of deuterium, in one of the, I think, multiple choice problems. And so you needed that mass again in a latter problem when I asked you about D2O, right? You need that to get that mass so you can figure out the moles of D2O. So it's there. That one you have to do around for somewhat, and that type of stuff happens. And I want to bring this out so you're aware of it. But did you know the formula for ethanol I gave? You know, and so if you're coming to lose a half a point because I give you the formula for ethanol, then you know I understand there's that tunnel vision. You know, and you might not have, you know, it might not click, but it was there in the exam. The formula for ethanol was there. And so be aware of this so it doesn't happen to you, because it happens every semester after semester. And it's always, well, it's not really that big of a mystery because it's just stress, I think, in the exam, and it's hard to think about that type of stuff. Well, anyway, so you're not only getting the periodic table, but you're getting a lot more. And so you should use those things to full advantage. You know, if I ask you the formula for, because in the next test, you're going to, I'm not going to give you the formulas of anything. I'm just going to give you names, and you have to come out with the correct formula. But fortunately, most of them are here and here, and so that can ease your memory burden somewhat. So anyway, what we're doing today is we're going to cover, let's see, chapter 5 next. And since I'm doing this with this camera here, I'm just going to write on this part of the board here. Is that all right? Or I'll have to pan this over, but I think it's not going to. Not going to get it. And I'll try to write big so you can see it better. But chapter 5, and there's something called Chem Compact B, Chem Compact G. Have you ever heard of those? Those are in the lab manual. So this is chapter 5 plus lab manual. The lab manual goes in much greater depth than our book does. And so you can find supplemental reading there. But I'm not going to follow either very closely. I'm not going to follow chapter 5 all that close, and I'm not going to follow Chem Compact B because I reorganized it. And so let me give you an outline of the organizational scheme here. The first part is the same, electrolytes. We'll be talking about those electrolytes, and then we're going to get into chemical reactions or chemical properties, and we're going to look at the different types of chemical reactions. What are the types of chemical reactions that we have? Well, we're going to start with metathesis, and then after metathesis we're going to cover acid-base. There are two types of acid-base reactions that we're going to look at. One is called the Bronsted. Do you remember a Bronsted, what a Bronsted acid is, or Bronsted base? Yeah, proton donor, acid, proton acceptor, base. And then we're going to look at Lewis acids and bases, and Lewis acid-base reactions. Does anybody recall what a Lewis acid-base is? It's not electron transfer. Electron transfer would be a redox reaction in which the electrons are transferred from one atom to another.
The H plus ion?
It's not just H plus would be Arrhenius or Bronsted. It's electron pair donor. Even though it donates, it doesn't completely lose them. You know, in a redox reaction, it completely loses it. And so there's a winner, there's a loser. But in a Lewis acid base, you know, it donates and then they share, kind of thing. Does that make sense? And so it's a little different. Well, it turns out that all acid-base reactions are Lewis acid-base reactions, all of them. Only a fraction of acid-base reactions are Bronsted. And so if you want to understand every single acid-base reaction there is in nature, then you should understand Lewis. Right? Well, if Lewis is the full comprehensive definition of an acid-base reaction, then why do we need Bronsted? Because Bronsted, if you understood all Bronsted reactions, let's say you understood all of them, all the Bronsted reactions, well, all the Bronsted reactions are only a fraction, you know, a small fraction of all the possible, all the possible acid-base reactions. And so why bother with Bronsted? Because Bronsted, you're just limiting yourself to a narrower range, a narrow number of reactions. So the reason we're going to even bother learning Bronsted is because Bronsted is so easy. Lewis is more difficult. Lewis is more work. And since Bronsted is so easy, if it fits the Bronsted category, we can just figure out the answer very quickly, rather than drawing out the structures and looking how it reacts in the Lewis acid-base sense. Okay, and then we're going to redox. For redox, there's single replacement redox. Right, that's a pattern that you learn in Chem 4. What's the pattern? Actually, I don't have to spell it. Yeah, element plus compound A plus BX yields AX plus B. It's a familiar pattern, and so you memorize this pattern, but there's a problem with this. There's two problems with this. Well, actually, there's more than two problems. The single replacement, not everything fits this pattern. For example, did you know this pattern fails for certain types of compounds? And so, you probably didn't memorize this, did you? I don't know, Sierra, did I ever mention about this? It was BX. If BX is an acid, did you know there are two types of acids that we deal with? There's the mineral acids and the oxidizing acids. Have you ever heard of oxidizing acids? Have you ever heard of an oxidizing acid? No. And therefore, how can you use this when one of the exceptions is that this doesn't work for oxidizing acid? Did you memorize that exception? Probably not. Or did you memorize that if the element A is a halogen, X2, then we have to use a different pattern? Did you memorize two single replacement patterns, the X2, 2BY pattern? Did you memorize that? Well, lots of people don't have it memorized, and lots of people end up with the wrong answer because they try to do the one size fits all Unfortunately, it doesn't. You know, and it's okay in Chem 4, because in Chem 4, what you can do is you can ignore all the exceptions. You know, it's the easiest thing to do is never mention them. If you never mention any exceptions, then there's nothing to worry about. And whenever you write a test or do something, you got to make sure you don't include one of the exceptions, otherwise you might get the wrong answer. Right? But you know, that's not the way. What we want to do is we don't want to be stuck in the in the kiddie playground. We want to go into the bigger playing field, right? And so now what we're going to do is either we're going to memorize these patterns and memorize the exceptions, or we're going to try to come up with a more general way of predicting these. One that we don't have to memorize the exceptions. Let me tell you about this. For example, ethanol, ethanol C2H6O, right? Well, so what's the oxidation state of carbon in ethanol? The oxidation state of carbon in ethanol is +6 minus 2 is +4 is -2. And so each carbon has a -2 charge. Is that accurate? It's not accurate, right? And so this is it. If you follow this set of rules, the 7 steps of oxidation state, you get this number. This number is not accurate. This number is an average, which I've been hammering down, but a lot of people don't think it's an average. A lot of people think that's the accurate number, right? And so what we came up with is we came up with a more general one. So you would have to memorize. If you really wanted the oxidation states of each carbon in ethanol, you'd have to memorize it's -3 and -1, which averages to -2. Do you want to memorize that? Just like, do you want to memorize all the exceptions here and here? No. You don't want to do that, and so it's better to come up with a more general procedure for figuring this out. And so the more general procedure is it requires more work. This requires more work because we have to draw out the Lewis structure, but at least we don't have to memorize all these things. I mean, who wants to memorize -3, -1, etc. For every nobody. And so here it's easier to see. This would be the general, right, method for figuring out the oxidation states. And here the rule is very simple, right? Winner takes all. And you don't have a bunch of exceptions. In fact, we have pretty much no exceptions that you have to memorize. And so what we're going to do is, if it fits this pattern, it's quick. Just like if it fits this is quick. This isn't that hard, and it doesn't take much time. This takes a lot more time, right? And so if it's quick, and we know it's not one of the exceptions, then go ahead and use this form, a plus bx, because you can get the answer very quick. It's going to be ax plus b, right? Or x2 plus 2by yields y2 plus 2bx. It's very quick and easy if it's not one of the exceptions, right? And so as long as you know what the exceptions are, this one fails for oxidizing acids. I mean, basically with an oxidizing acid, you would predict that there's no reaction when in fact there is a reaction, and it isn't this single replacement form. And so what I want to do is I want to show a more general method. I mean, was this in the book here? This method? For figuring out the oxidation state, was that in the book? Sorry. No. All right, this method is not in the book either. And so, but it's not difficult. Is this difficult to learn? Maybe, but after you do a bunch of them, it's not difficult. And so what we're going to do is we're going to kind of replace this and come up with a more powerful method that we can use to solve a lot of redox problems. And the more powerful method, since I don't have a good name for it, is I'm just going to call it the chart method, but This is nothing that I invented. This has been used by many people well before me. And so we'll just call it the chart method. All right, so it just gives you more tools to use in analyzing this. Of course, you can still use single replacement form and others. And then we got single replacement, and then what other types of reactions do we have? We have combustion, right? We have element plus element combination. Decomposition, which is the reverse of combination, etc. And then we have one other one.
Double replacement.
Double replacement is, not redox. Not redox. Double replacement would be metathesis. And then we have skeleton redox. The nice thing about skeleton redox is you don't have to predict the products. In skeleton, the products are given. We just have to balance the equation. In these others, we have to predict the products. All right, so this is what we're going to be talking about for chapter 5. And this is pretty much just how it's going to be organized. Just the electrolytes and then chemical properties, one by one. So you'll have to review electrolytes. And so let's do that right now. Let's see. There are like 3 types of electrolytes. What are they? Strong, weak, and none. All right, let's go to strong electrolytes. What are strong electrolytes?
They completely disassociate.
They completely dissociate. And so, actually, did you know there are 2 definitions for a strong electrolyte? Let's talk about definition 1. Definition 1. Complete dissociation or complete, there's another word for dissociation, ionization. And so complete ionization. And then definition 2. Definition 2 has to do with people who work in electrochemistry. They're looking at batteries, or they're looking at conduction of electricity or ions. And so for them, a strong electrolyte is an excellent conductor. And so we call it, definition 2, high ionic conductivity. And so if we look at this, if we look at sodium chloride, is sodium chloride a good strong electrolyte? Yeah, sodium chloride is a good electrolyte because when it dissolves in water, it dissociates or ionizes completely. And a sodium chloride solution, does it have good electrical conductivity? Yeah, in fact, a sodium chloride solution can conduct electricity as good as copper metal. Copper metal is kind of the benchmark for electrical conductivity. And so you could have a salt water that conducts just as good as a metal, copper. However, what if the sodium chloride were extremely dilute? What if it was almost pure water and then you just sprinkled a few crystals of sodium chloride in your pure water? Would that conduct electricity very well? No. And so, very dilute solutions of sodium chloride would meet definition 1, but would fail definition 2. And so it depends on what type of chemistry you work in. If you're working with batteries and electricity, then all you care about is definition 2. You don't necessarily care if it completely ionizes, because what you can have is you can have something that isn't very soluble. You can have something that has very, very limited solubility, but when it does dissolve, it breaks up into ions completely. You know, with something like that, something with very limited solubility that breaks up 100%, it's a strong electrolyte, right? Well, it depends on who you talk to. You know, some people will say, yes, that's a strong electrolyte because it completely ionizes. Other people you'll talk to say, no way, that's not a strong electrolyte because it conducts so poorly. Well, let's take a look at weak electrolytes. Well, what are the strong electrolytes? Tell me what strong electrolytes are. And what are we going to focus on? Which definition do you think we'll target? Definition 1. Definition 1. You know, a lot of people get solubility and electrolyte properties mixed up. If something's highly soluble, is it a strong electrolyte? No, like sugar. Sugar is highly soluble, but does sugar water conduct electricity as good as copper? No, not at all. It would be a pretty bad conductor, unless there's some other ions in there. And some things don't even have to dissolve. For example, there are insoluble compounds that are strong electrolytes. Did you know that? How can an insoluble compound be a strong electrolyte? Well, a lot of battery research is trying to get away from what they call aqueous electrolytes. And they're trying to go to non-aqueous or solid electrolytes. Especially because water is very heavy, for one, and it has a temperature limit. You can only heat it to about 100 degrees C, right? And then it'll start to boil. And so that's a big problem because some batteries operate, well, more efficiently at high temperature. It's high temperature cells. For a high temperature cell, you cannot use an aqueous electrolyte. And so what they have is they have solid electrolytes. These solid electrolytes actually conduct ions through channels in the crystal structure, and they conduct ions so well that their conductivity, electrical conductivity, for some of them are as good as copper, and for others exceeds copper electrical conductivity. And the ones that exceed are called superionic conductors, because ions can go through those channels with minimum resistance. Well, anyway, so getting back to this, we'll focus on definition 1. And so going on to what are strong electrolytes, tell me what strong electrolytes are. They are how to recognize a strong electrolyte. Like sodium chloride is one, but what else is a strong electrolyte?
Alkaline metals.
Alkaline metal? Alkaline metal compounds or just alkaline metals?
Just alkaline.
Alkaline metals are not because electrolytes you need ions, and so the alkaline metals themselves won't conduct because they're neutral unless they react. If the alkaline metal reacts with water, then it'll make a good conducting solution. But it's because of the sodium hydroxide in there. It's not because of the alkaline metal. So what are the strong electrolytes? Did I tell you about my friend who is studying for the MCAT? No? My friend who is studying for the MCAT is mostly general chem and a little bit of organic chem. But he had taken general chem so long ago, he came to me for help. And so I started going through it with him, some of the old topics. But clearly, it was impossible. There was no way he would have been ready to take the MCAT. This was like four months later. It seemed because he forgot everything. Absolutely forgot everything. Which is easy to do, right? So if you're planning to take the MCAT, some people mentioned that they're going to start studying for the final, right? And that's a great idea. But, you need to take this a step farther. If you're planning to take the MCAT or the DAT test or whatever, what you want to do is you want to be flipping through your notes, not just until the final exam, but you want to be flipping through your notes, like on a regular basis, all the way up until you take that test. right? Otherwise, you're going to forget like he did. He had to take a year off to go back through. I mean, he took it and he didn't do well, but he had to take a year off and go back through everything because God, it's so easy to forget. And so, anyway, it's like this, you know? I asked him, well, what are the strong electrolytes? Don't know. No clue, you know? This is like Chem 4, right? You learned in Chem 4, but it just faded away already. Unless, maybe it didn't fade away. Tell me how we recognize the compounds that are strong electrolytes. What are the strong electrolytes?
Strong acid.
Strong acids, good. So we're looking for strong acids. Okay, what are the strong acids?
Chloric acid.
Perchloric, hydrochloric,
Bromic. Hydrobromic.
hydrobromic, hydrate. That one you don't have to memorize because I'm giving you this chart here. This has 6 of the 7 strong acids, so it's not that bad. Right? Okay, so you memorize the 7 common strong acids. Most other acids are weak. There are many more, actually, strong acids, but we're not going to worry about those because those aren't as common. So strong acids, most people, no problem, right? This is where people have problems. Strong bases. What are the strong bases? Tell me. Lithium hydroxide, sodium hydroxide, potassium, calcium hydroxide. Is that it? No, that's not it. Keep going. Okay. Amides, good. Amides. What else? Rubidium hydroxide? Ammonia? No, ammonia is not there.
It is. Right there.
Where?
It's more of
This? We don't consider ammonia a strong base. We consider ammonia a weak base. The dividing line between weak and strong turns out to be hydroxide. Bases that are weaker than hydroxide we call weak. Hydroxide and bases that are stronger than hydroxide we call strong. And so here I had it right, amide. Amide's the strongest on this chart, NH2 minus. Then oxides, hydroxide. Sulfides are out of place here. Sulfides actually belong down here with the strong bases. And so the strong bases on this chart are the amides, the oxides, the sulfides, and the hydroxide. Phosphate is close, but not quite there. And so how would we classify this? Oh, this camera rotate. That's good. I don't have to twist my computer. So strong bases are the soluble hydroxides. What are the soluble hydroxides? Group 1, ammonium. Group 1, ammonium. Calcium. Strontium, barium. And so those are all strong bases. The soluble oxides. The soluble oxides would be the group 1, pretty much. And not calcium, strontium, barium. Those are insoluble. And then the soluble sulfides and the amides. Amides are pretty much all soluble. The amides. All right, strong bases and soluble salts. Okay, so we have complete ionization or dissociation for these species here. Then we go on to weak electrolytes. So what are the weak electrolytes and what do they do? So there are two definitions for weak electrolyte. What is definition 1 for a weak electrolyte? Partial or incomplete ionization. And definition 2? Yeah, weak conductors of electricity or weak ionic conductors. When we think about conducting electricity, the charge carrier normally is electrons going through a wire, but we could have ions either going through solution or ions going through some solid through channels in the crystal structure. And, both of those work. Okay, what types of compounds are weak electrolytes? Weak acids, good. Weak bases. Weak acids, weak bases, and some heavy metal salts. In some of these heavy metal salts, the bonding is more covalent than ionic. It's not like an ionic compound. So factor that in. Okay, what are the weak acids? If you memorize the strong acids, then we're just going to assume that all the rest are weak. That works, but there are exceptions. We aren't really going to worry too much about at this point. What about the weak bases? How do you recognize the weak bases? Well, the weak bases would be like on this chart: phosphate, carbonate, etc. A lot of weak bases. And so just consult the chart. All right, then we come up with the non-electrolytes. And so we have the strong, the weak, and the non. The non-electrolytes are pretty much everything else, right? Pretty much everything else. And what do the non-electrolytes do? They don't conduct. In definition 2, they don't conduct. They don't conduct is definition 2. Definition 1 is they don't ionize. All right, now here comes some tricky stuff. So some tricky stuff is you could have a weak electrolyte that conducts electricity very well. And so, for example, even though it just partially ionizes, if it's highly soluble, you can get the concentration of ions so high that it conducts just as good as copper metal. And so in that case, it would be a weak electrolyte in terms of ionization, but a strong electrolyte in terms of electrical conductivity or ionic conductivity. Does that make sense? And then you could have strong electrolytes, but because the solubility is so low, even though they're strong electrolytes, you generate so few ions that the electrical conductivity is quite weak. And so it could actually be classified as a weak electrolyte or even a non-electrolyte. Does that make sense? Because think about if you had a gallon of distilled water and then you put in 1 part per trillion sodium chloride, do you think it's going to conduct electricity very well? No, not at all. It's going to be pretty much an insulator, even though it has a strong electrolyte dissolved in it. And so those are the types of things we think about when we're thinking about electrolytes. Next thing I want to talk about carries this further. And that is this term ionization, And so that was electrolytes, and now we're going to look at ionization or dissociation versus hydrolysis. Whenever we're thinking about electrolytes, we've got to figure out what happens to the species. Like, for example, if you have sodium chloride does what? Sodium chloride breaks up into sodium ions and chloride ions. Right? And so let's take a look at ionization. An example of ionization would be something like HCl. HCl is a strong acid. Strong acids are strong electrolytes. Strong electrolytes should ionize or dissociate completely. What does it dissociate into? H plus and Cl minus. H plus. What is H plus? H plus is a hydrogen ion. What's the hydrogen ion made of? Hydrogen ion is made up of how many protons?
One.
How many neutrons? 0 for the most common. And how many electrons?
One.
None, because it's lost it. And so what this is just a proton. Is a proton big or small? Extremely small. Extreme. Even though the charge isn't so big, it's just got a +1 charge. That +1 charge is concentrated on an extremely minute, extremely small volume, which means that it's going to be reactive or not that reactive. It's reactive. Protons are terribly reactive. And so protons, free protons like this, that is protons floating around in aqueous solution, don't exist. You know what that proton's going to do? It's going to react with something immediately. Do you know what it will react with immediately? Water. And so when we see a proton like this, this is too unstable. It really doesn't exist in this form. It's really H3O+. What's H3O+ called? Hydronium. And so this is not accurate, but we still use this because it's a nice compact equation. And really, does the proton just fall off the HCl?
No.
No. Really, something collides with it or something pulls it off. And so hydrolysis is more appealing because hydrolysis, we have a water come in, and the water plucks the proton off. When the water plucks the proton off, we form hydronium and chloride ion. Hydronium and chloride. And so we have ionization versus hydrolysis. Hydrolysis is much more accurate. This is more accurate. This is more accurate, but we still use this equation often. You look at those reactions there, they're all ionization reactions, dissociation reactions. Why do we use this? Because it's easy, it takes up a lot less space. And so we continue to use this. This is kind of the shorthand. Method. This is the longhand method here. The longhand method's more accurate. Okay, there could be other species, hydronium, etc. They looked at these clusters that form to help stabilize the proton. All right, so when we talk about strong electrolytes, we either say they ionize 100% or they hydrolyze 100%. Complete hydrolysis, complete ionization. If we have a weak acid, like acetic acid, we can do the same type of deal. Acetic acid in terms of ionization would look like this. It's going to form H plus H2C plus H plus C2H3O2 minus. But since this is weak, sometimes we'll draw these uneven arrows like this. Not always, but sometimes we'll draw it like this to show that the molecules are favored. It's very hard for that proton to dissociate. And so that proton's kind of stuck on there. But a little bit of them will be dissociated. Maybe there's a collision that causes this. And so this would be the ionization. As far as hydrolysis goes, we get partial hydrolysis here. That is, the acetic acid plus H2O liquid partially hydrolyzes into hydronium and acetate. right there. All right. Okay, give me a strong base. Okay, another one. Actually, let me give you a strong base. Let's do sodium. Would you say sodium hydroxide is a strong base? Okay, what's sodium hydroxide going to do since it's a strong base? It's going to ionize or hydrolyze 100%. And so this seems to fit. We take sodium hydroxide, it ionizes into sodium ions and hydroxide ions, correct? But I want to shift your way of thinking about strong bases. Strong bases are tricky because sodium hydroxide, I don't visualize that as the strong base. The strong base to me is this, the hydroxide. This is the strong base. This is what I call soluble salt. Soluble salts are strong electrolytes, and soluble salts will ionize or dissociate 100%. And so if hydroxide is a strong base, how does hydroxide ionize 100%? So for example, if I had sodium amide, this would be sodium amide. Sodium amide would ionize 100%. Sodium plus and amide minus. Amide is just NH2 minus. And so we got complete ionization there. But is this complete ionization because sodium amide is a strong base, or is it because sodium amide is a soluble salt?
Soluble salt.
It's a soluble salt. All sodium salts are soluble. And so the strong base part of it is the amide. Strong base. This is soluble salt, right? Okay, let's go to ammonia. Ammonia is a weak base. Weak bases partially ionize, partially hydrolyze, right? And so this being a weak base, this is not a soluble substance. This is a weak base, it's a soluble compound. Now you tell me, how does ammonia ionize? What does it ionize into?
Ammonium.
Okay, ammonia ionizes into ammonium and
Hydrogen ion.
hydrogen ion. Okay, when we try to balance equations, we got to make sure the atoms balance and the charges balance. Are these balanced?
No.
No, so this can't be. I mean, we could put two ammonias there, but it still wouldn't balance. We got +2 on the right and 0 on the left. Not going to balance. What will it ionize into? It's a weak base, so it partially ionizes, right? What does it ionize into? H plus and NH2 minus? Is that what it ionizes into? Yes? No. For bases, this is what. Bases, we're going to say do not ionize. Don't try to ionize a base. Instead, what bases do is they're going to hydrolyze. And so let's take these three bases here. The first base is not sodium, the first base is hydroxide. Hydroxide is a strong base, right? It's on the chart there. It's number 3 or 4 on the chart. And so if hydroxide is a strong base, how does hydroxide ionize? How does hydroxide ionize? H plus and oxide? No. We're not going to ionize. You're going to say bases do not ionize, bases hydrolyze. And so hydroxide being a strong base will hydrolyze water completely. And so when hydroxide hydrolyzes water, what forms? Hydronium. Not hydronium. Okay, what's going to happen is, there's no extra, what's going to happen is this, the hydrogen is going to be transferred to, so we're going to form water and hydroxide. Water and hydroxide. That's going to be what happens. It can't go to hydronium. Let's say it went to hydronium. Then it would form oxide plus hydronium. Right? That's what you got. But compare the two driving forces. The driving force for this is an acid-base reaction, by the way. An acid-base reaction is going to have a driving force of going from a stronger acid to a weaker acid. So here, what's the acid? The acid is the proton donor. It's going to be water. And so we go from water to hydronium. Which one is a stronger acid? Hydronium or water?
Hydronium.
Hydronium is a much stronger acid. So what's happening is we're going, and this is what we got to talk about, and I forgot to mention this, about why I classify the reactions in this way. Did somebody figure out why I classified into 3 categories? I classified them into 3 categories because of their driving force. You know, there are 3 types of driving forces that we're going to look at. And when we're thinking about a driving force, what is a driving force? Yes. The driving force is like stronger to weaker acid. Driving force is like precipitation. Driving force is going from a more active element to a less active element. The driving force is gas formation. But does gas formation work for all types of reactions? No. Does stronger acid to weaker acid work for all types of reactions? No. And so we got to think, what types of reactions do those work for? For example, do all combination reactions have the same driving force? No. There are some combination reactions that will have one type of driving force and other combinations that reactions that have another type. And so rather than thinking about all that, it's I think easier to learn it based on driving force. And the driving force is, overall, what you're trying to do is you're trying to go from something that's less stable, more reactive, to something that's more stable, less reactive. And so in terms of gravitational energy, this would be higher gravitational energy, this would be lower gravitational energy, right? And the same thing with like chemicals. There are some chemicals that are so reactive, it's like having a rock, you know, perched precariously over your head. You know, at any time it's going to fall down and hit you. Right? These chemicals are so unstable. And so what we're looking for is, you know, trying to go from less stable to more stable. But in this particular reaction, in the second one, oxide to hydronium here, we're actually doing the opposite. You know, hydroxide and water is a heck of a lot more stable than oxide and hydronium. You see, so there's not much driving force for this. Whereas there would be a better driving force for this. But when you look at this reaction, did anything happen? No, nothing happened. And so essentially it's basically no reaction. Although we say that there's no reaction here, the collisions don't stop. You know, hydroxides will collide with water, And there will be this proton exchange, but we end up with the same thing. And so that's hydroxide. All right, this is a strong base. The next strong base is amide. This is a strong base. And so a strong base like amide does what? Does it ionize completely? Does it dissociate completely? No, it's going to hydrolyze completely. And so when amide hydrolyzes water, what happens? It's going to form ammonia and hydroxide. And so here we're going from a stronger base, amide, to a weaker base, hydroxide. And so we have this driving force here that's going to drive this reaction to completion. And therefore we call amide a strong electrolyte. It hydrolyzes water completely. How about ammonia? Ammonia doesn't ionize. Ammonia is a base it's going to hydrolyze. And so when we look at ammonia and water, what does it form? Ammonia and hydroxide. And so take a look. A strong base like amide and a weak base like ammonia produce the same product. The same product is hydroxide. And so shouldn't they be equivalent in strength? No. Well, the difference here is this. There was a good driving force for this reaction, right? Is there a good driving force for this reaction? No, because we're going from, this is our base, it's the proton acceptor. This is our acid, the proton donor. And so we're going from the acid water to the acid ammonium. And so what's a stronger acid, water or ammonium? Or we're going from the base, this is the base, ammonia, to the base hydroxide. Which one's a stronger base, hydroxide or ammonia? Hydroxide. And so do you see there's no driving force here? We're going from something that's more stable to something that's less stable. So typically what we'd say is that there's no reaction, right? But that's not always the case, because what happens is this. When you mix these things together, there's a lot of motion, there's kinetic energy, and we have collisions occur. And the collisions never stop. Now, we have to think about these collisions. The collisions that occur here between ammonias and water molecules, are they all exactly the same? That is, are all the ammonias moving at the exact same speed, and are all the waters moving at the exact same speed, so all the collisions are identical? The answer is no. Do you guys remember the Maxwell-Boltzmann distribution? Actually, maybe you've never heard of it. Sierra, do you remember the Maxwell-Boltzmann distribution? No? Or the thermal, or the temperature distribution? Okay, what happens is this. Are all the molecules in this room moving at the same speed?
Yeah.
No. Even though this room has a stable temperature, at this given temperature, we call it room temperature, not all the molecules move at the exact same speed or at the same energy. Some molecules are moving very fast, some are moving slow, but the bulk of the molecules are moving at some speed, which gives us a particular temperature here. And so this distribution is called a Maxwell-Boltzmann type distribution. It looks like a bell curve, except it has a long tail on the side here. And You learn about this with gases, the speed of gas molecules. Well, the thing with this is it's the same thing with water. If I had a beaker of water, are all the water molecules moving at the same speed? No. Some are moving fast, some are moving slow, but the bulk of them are moving at some average, which gives it that temperature. And so the situation here is that we can't turn off the collisions. The collisions are going to happen. Ammonia is going to collide with water, but most of the time when ammonia collides with water, nothing happens. It just bounces off. But once in a while, you get a highly energetic ammonia and a highly energetic water, and they collide with some force. They're not forced to break the bonds. And so that happens, and that happens to a small extent depending on how strong the bonds are and how unstable these are. And so what we say is there's partial reaction. Even though we don't have a driving force here, we're going to get a little bit of reaction because we can't stop it. Now sometimes it's so lopsided we're going to get no reaction. This would be way too lopsided. To create these are extremely unstable species. And so to create something this unstable, like the oxide and hydronium over here, to create something that unstable would require very high energies. And as we get to very high energies, the population really cuts way down. And so this might be the energy cut off for an extreme reaction like this. But there's so few molecules capable of that, and the probability of those collisions is so small that reaction really doesn't happen. Whereas this reaction here, no problem. Or this reaction here, maybe the cutoff is about here. And so you have a good population of molecules that can actually collide with enough energy to form these unstable species here. So in other words, it depends on how big of a difference in stabilities there are. If there's a huge wall, then it's likely not to happen. But if it's just a small barrier, then we can get partial reaction and see this happen. All right, so we have partial hydrolysis here, which forms this. And so in other words, the stronger the base, the more hydroxide we generate in solution. And it turns out hydroxide is the strongest base that can exist in water. What do you think the strongest acid that can exist in water stably is? It turns out it's hydronium. And so this brings us to the next topic I want to talk about, and that's the leveling effect. This is, in Chem 4 I only talked about the leveling effect of strong acids. Now I want to add the leveling effect of strong bases to this. But if you aren't familiar with the leveling effect, it goes like this. What's stronger, HCl or HNO3? What's a stronger acid? We look at the chart, and it turns out HCl is a stronger acid. And so HCl is a better acid. We react that with water here, and we're going to form what? Well, strong acids do what? They hydrolyze completely to form hydronium and chloride in this case. HNO3 is weaker. HNO3 is weaker, but it's plenty strong to react completely with water to form hydronium and nitrate. And so maybe one analogy to this is this. I don't know if this is the best analogy, but this is what I thought of this morning. But those, if you go to like a carnival or a fair or something and they have a strong man or a strong person booth where you hit the hammer on this and this weight shoots up, and if you hit it strong enough or hard enough, it'll hit the bell at the top, right? Okay, so what this is like is this is like if you have two very strong people, HCl and HNO3. And so the HCl person comes over here and hits it, and it goes and rings the bell. The HNO3 person comes here, hits it, it's going to ring the bell as well, right? And this would be complete hydrolysis. if somebody moved the bell higher, then HCl would be able to knock it even higher, but the bell is already set so low that both of them can easily hit that. And so it doesn't matter, is there an acid stronger than HCl?
Yeah.
Yeah, what is it? For example, HClO4. HClO4 is at the top of our chart. What's this called? Perchloric acid. So if perchloric acid came over here, even though perchloric acid is a stronger acid, is it going to make any difference? No, it's going to ring the bell here. And so that's the max that we can do. And so it's the same thing. You know, when we react with water, there's nothing more we can do. It's already maxed out. We have to react it with something else to really show the difference between HNO3 and HCl. You know, because it's too small of a playing field. Does that make sense? Whereas something like acetic acid comes along here. Acetic acid hits this and it only goes up this high. You know. Or phosphoric acid comes here. Phosphoric acid almost hits the bell, but can't quite get there. You see that? And so the weak acids will be in some range here. The stronger the weak acid, the higher up it will go, but it won't hydrolyze completely. And the weaker the weak acid, the lower down it goes, and we form less hydronium. And so in other words, with the strong acids, all the strong acids are going to yield the same amount of hydronium. Therefore, all strong acids in water are the exact same strength. And so water, well, I guess water, another way of thinking about this is water is a weak opponent. You know, if you had an opponent that's more difficult, that's going to cause you more trouble, then there might be a difference between HNO3 and HCl, or HNO3 and HClO4. But since we're dealing with water, no difference. It's easy to overcome. It's just when we get to phosphate, and you can see phosphate there with the border, that's when things start to be differentiated. Okay, that's the leveling effect for strong acids. What about for strong bases? Well, it turns out the strongest acid that can exist in water is hydronium. So any acid stronger than hydronium gets converted to hydronium. And so HCl doesn't exist in water as HCl. You know, it would react to form hydronium and chloride. Same thing with nitric acid. It doesn't exist as nitric acid. Now the bases do exactly the same thing. If I had amide, you know, what does amide do? Amide's a strong base. Strong bases hydrolyze water completely. When they hydrolyze completely, they're going to form ammonia and hydroxide. And so here I have hydroxide. I'll take another strong base. Let's take a strong base like sulfide. If I take sulfide, which is out of place on that chart, but sulfide is a very strong base. I react it with water. What's going to form? HS minus and hydroxide. And you see we're going to form the same amount of hydroxide in a complete reaction. It's just a 1-to-1 mole ratio. And so these are equivalent here. Therefore, this is called the leveling effect. Strong bases. It's a little bit more tricky for bases, but basically we'll boil it down to this. All strong bases have the same strength in water for a given concentration. Okay, of course if we change the concentration. So, you know, my high school chem teacher used to always say, you know, he'll drink some HCl. Did I tell you this story?
Yeah.
Yeah. After neutralizing it with sodium hydroxide. But, you know, I've drank HCl without neutralizing with sodium hydroxide. It just happened to be so dilute that it's coming out of the tap. But anyway, yeah, for a given concentration, I have to add that on there, of course, because if you had, let's say, 6 molar HCl versus micromolar nitric acid, then there's going to be no comparison. 6 molar HCl will easily beat micromolar nitric acid in terms of acidity. Okay. All right, that's the leveling effect. Now let's talk about the first type of reaction. The first type of reaction that we're going to deal with are metathesis. Metathesis reactions, we also call these AKA what? Favorable ion combination. And so what makes a favorable ion combination? Well, this is a case where the ions come together. And so one of the things that make this, we call this the driving force. All metathesis reactions are going to have a similar driving force. We're looking for what favorable ion combinations there are, and one of the clues that it's a favorable ion combination is precipitation. If the ions come together and they stick together, and stick, and build larger crystals, eventually that will precipitate. And so the ions are going to come together for precipitation. What are the things that precipitate? Well, if you know the solubility rules, then you have most of them. Yeah. So just memorize your solubility rules. And then another thing, when ions come together to form a gas, that's very favorable as well. Gas formation. So these ions come together. As far as gas formations go, some form gases directly, like hydrogen ions and sulfide ions come together to form H2S, which has a rotten egg odor and it's very toxic. Others will form, like for example, a favorable ion combination would be hydrogen ions with carbonate ions, and that forms this acid. What is this called? Carbonic acid. And then we have a decomposition reaction occur. H2O liquid plus CO2 gas. Do you guys memorize that?
Yeah.
Yeah, is this decomposition a redox decomposition? Or metathesis decomposition? Okay, let's answer the first one. Is it a redox decomposition?
No.
No. Why? None. The oxidation states don't change. All the oxidation states are the same. Is this a metathesis decomposition? No, because in metathesis decomposition, you break the ions apart. This is different. This must be a not a combustion is redox, actually. This must be this process of elimination. It's not metathesis. It's not acid-base. Or no, I got it wrong. It's not redox. It's not metathesis. It must be. It is acid-base. This is acid-base. That's an acid-base decomposition reaction. Does it look like a simple proton transfer to you? No, this is Lewis type acid-base reaction. Anyway, we have the ion combination. The ion combination makes carbonic, and then we have an acid-base type decomposition to form H2O CO2. How about this one? Ammonium hydroxide. Do you know what that decomposes into? Ammonia and water. Now, ammonia can be aqueous or gas. And then there's one more. Do you know the last one that you're supposed to memorize?
Sulfurous acid.
Yes. Sulfurous acid has the formula H2SO. Not 4. Yeah, 3, because 4 would make it sulfuric acid. This is sulfurous acid. Sulfuric acid doesn't decompose like this. Sulfurous acid will decompose into water and sulfur dioxide gas, also a toxic gas. And so these are the ones that people recognize from Chem 4. And then we continue on. The last driving force we're going to look at is going from a stronger acid to a weaker acid. And so, what's stronger, acetic acid or hydrofluoric acid? That we just look at the chart, the acid chart. So you work in conjunction with the chart to determine. It doesn't have to be a strong acid, just a stronger weak acid to a weaker weak acid is perfectly fine as well. Okay, so let's do an example of this. We're going to start off with a tricky one. The one we're going to do is this. We're going to take this, magnesium chloride. And on a test, I'm not going to give you the formula MgCl2, I'm going to give you the name, magnesium, Mag, etc., chloride, and then you have to figure out the formula. So after doing that, you figure out, okay, MgCl2 and aqueous ammonia, NH3AQ. AQ I leave off. All right, what type of reaction does this look like? Does this look like a single replacement reaction? No, because a single replacement would be a compound plus an element. Does this look like a double replacement?
Yes.
Not really, because double replacement is a ionic compound plus a ionic compound. So it would be AB plus CD. The ammonia is not an ionic compound. Ammonia is a molecular compound, right? And so this is molecular. And when we're thinking about metathesis are favorable ion combinations. So where are the ions? We need the ions here. We've got to look at what ion combinations are favorable. And so where are the ions? Well, it turns out this is metathesis. This is metathesis because ammonia is a weak base, and weak bases do what? Weak bases partially hydrolyze water. So when ammonia hydrolyzes water, what forms? Ammonium and hydroxide. And so the ions are there. They're a result of this reaction. What kind of reaction do you think this is? This is a hydrolysis reaction, which would be a redox, acid-base, or metathesis, acid-base. And so as a result of this hydrolysis reaction, we get some ions formed. And so what should we do? Should we write magnesium chloride plus ammonium ions plus hydroxide ions, or in other words, should we write magnesium chloride plus ammonium hydroxide? Should we write that? No, we're not going to write this like this. The reason we're not going to write this like this is because you need to buy chemicals. When you go buy the chemicals and you ask, I'd like to buy, let's say, 1 molar solution of ammonium hydroxide, are they going to have it for you? No, they're going to tell you that ammonium hydroxide is it stable? No, ammonium hydroxide is unstable. It's going to decompose into, immediately it'll decompose into ammonia and water. And so, if you try to get this, you're out of luck. What you can buy, however, is you can buy ammonia, which is a gas, and then just dissolve it in water. And so you can buy aqueous ammonia, no problem, there. And so I don't want to see ammonium hydroxide in place of aqueous ammonia. You can write ammonium hydroxide here to help you because it fits the AB plus CD. We know we're going to get some ammonium and hydroxide ions from hydrolysis, just a little bit, right? And so if it's an AB plus CD, what do we form? Well, magnesium chloride plus ammonium hydroxide forms magnesium hydroxide and ammonium chloride. Okay, now we need to balance this. We need 2 of these ammonium hydroxides, which means we need 2 ammonias and 2 waters. And this will form 2 ammonium chlorides. Now, is there a driving force? Yeah, magnesium hydroxide is insoluble. This is a precipitate, and that would be our driving force here. Okay, next what we're going to do is we figured out the reaction here. Again, we're going to leave it as ammonia and water, not this. But this. Okay, this is called our complete equation, or conventional equation. And then what we're going to do here is we're going to come up with an ionic equation. In the ionic equation, we ionize the strong electrolytes. So when we ionize the strong electrolytes, is magnesium chloride a strong electrolyte? Yes, it's a soluble salt. So we ionize it to magnesium 2+ plus 2 chlorides. Is ammonia a strong electrolyte? No. So we leave it alone. We get +2 ammonia. Is water a strong electrolyte? No. Leave that alone. Is magnesium hydroxide a strong electrolyte? No. So we leave that alone. Is ammonium chloride a strong electrolyte? Yes. So we ionize it. 2 ammoniums and 2 chloride. We got to make sure everything's balanced. So you'll see I make sure the coefficients are correct here. And then the last step is we generate what's called the NIE. You know, the NIE is, what does that stand for? Yeah, and we cancel the spectators. So we get rid of the spectators. We get Mg2 plus 2 ammonias plus 2 water liquids yields MgOH2 solid plus 2 ammoniums. And then we got to make sure that the NIE is balanced. So we check the atom balance. Atoms are balanced. We check the charge balance. The charge is 2 plus on the left and 2 plus on the right, so it's balanced. And that's what we're going to be doing for metathesis reactions. We'll be writing the CE, the IE, and the NIE for these and stating the driving force like this. And so an example of a metathesis there. All right, so hopefully this works, and with these videos, I'm going to post them in Chem 108 on one of the computers, probably the computer right next to the printer. And so what you can do is you can bring a flash drive or something and then just copy it if you want. I can't post these on Piazza because the file size is too big.